So the next section we're looking at is 2.5, is the derivative of composite functions. Before we get to the actual calculus portion, which is to look at the derivative, let's make sure we understand what is a composite function. A composite entity is any entity which is made up of multiple parts. So a composite function is a function that is made up of multiple other functions, or two or more other functions. So for example, let's say you have a function g at x, which is equal to x squared. And then you have another function f of x, or let's change that to f of a, which is going to be square root of a. Now, if we want to make a composite function, so for example, if I say y is equal to f of g at x, so f of g. So what this means, the composite function is one function that is made up of f and g. These two combine to make one new function, which in this case would be the outside function. The main function would be f, which is the square root, and we would replace a with g at x, which in this case is x squared. So it would be square root of x squared, and then we can simplify that to be just x. So understand, a composite function is any function that is made up or of two or more functions. Up until now, all we've dealt with has been polynomial functions. So to find the derivative of these, it's going to be very similar to what we've learned back in 2.1, in 2.2 when we did the power of a function rule. So if you were to find the derivative of a composite function, I'll take a separate example here. So if we have, say f at x is equal to 3x minus 4 squared. This is what we would have seen in 2.2 when we have the power of a function rule. We have the internal function and we have the external function. The internal function g at x would be 3x minus 4. The external function, the main function, is the square. So we take an internal function and we apply the external function of squaring that internal term. So 3x minus 4 squared. When we find the derivative, what we learned was we bring the 2 down. This becomes 3x minus 4. Subtract the 1 from the exponent, and then multiply all of this by the derivative of the inside of the internal function, 3x. Now this process, this becomes 6x minus 8 multiplied by 3, which will then be 18x minus 24. This process of finding the derivative uses this power of function methodology, can be applied to all composite functions using something called the chain rule. I'm going to explain the chain rule now, but if you can do this, you have already done the chain rule. The power of a function rule is a very specific example of the chain rule. So just like in this equation, in this part over here, I've explained what a composite function is. Let's look at how we would find the chain, how we would use the chain rule for composite functions. So if we are given a function which is f of g at x, meaning again we have a composite function where the external function is f and the internal function is g at x. To find the derivative, we would start by finding the derivative of the external function. So we would have to find the derivative of f. Leave the internal function exactly as it is. You would find the derivative of the external function, whereas the inside component, the internal component, stays exactly as it is. And that'll make more sense once we actually do the question. And then you multiply it by the derivative of the internal function. Up in all of chapter 2, you deal with polynomials only. So it's exactly the same as power of function rule. But as we move on to later equations or different types of equations, when we get to exponential functions or logarithmic functions or even trigonometric functions, the chain rule will become a little bit more important, a little bit more complex, as you will have different functions being applied. So far, all the functions will be the same. You'll have a polynomial within a polynomial within a polynomial, so the chain rule process will be exactly the same. So let's take a second example, and if we have let's say there's a function f at x is equal to 2x squared minus 4 to the power of 1 over 3. We have an internal function, g at x, 2x squared minus 4, and we have an external function, which is 1 over 3, which is the primary overarching function of you take whatever's inside and you take it to the power of 3, to the power of 1 over 3. So find the cube root. To find the derivative, we start by taking the derivative of the external function. So the 1 over 3 comes down. And we do 1 over 3 minus 1, so we get negative 2 over 3. The inside, the internal component of the external function stays exactly the same. So it stays as 2x squared minus 4. And then we multiply it by the derivative of the internal function, which in this case would be 4x. The process is exactly the same as the power of a function rule, but we're just looking at it a little bit differently. So if we continue to simplify this, what we'll end up with is 4x over 3 times 2x squared minus 4 to the power of 2 over 3. The new part now we're going to take a look at is how to use the chain rule. How is the chain rule applied using Leibniz notation? So let's take a look at that. So now we're taking a look at example 3. We're given that y is equal to u squared minus 2u plus 1, and u is equal to 2 times the square root of x. We have to find dy over dx at x equals 4. There are ways to do this. We can go ahead and just plug u into here, but that's not really using the chain rule. That's not using Leibniz notation. So using Leibniz notation, what we need to understand is to find dy over dx, we can use these two. Dy over dx means find the derivative of the function y where the independent variable is x. We don't have that. We have the function y where the independent variable is u, and then we have the function u where the independent variable is x. If we find the derivative of this function, we will get dy over du. If we find the derivative of the function u, we'll get du over dx. We need to find dy over du using, we need to find dy over dx using dy over du and du over dx. If we use what we know about algebra and just working with fractions, we know that if we multiply these two, the du and the du will cancel out, and we'll be left with dy over dx. So what's the simple solution here? To find dy over dx, we can find the derivative of y, find the derivative of u, and multiply them together, and that should give us dy over dx. So let's try this. The derivative of, so dy over du will be 2u minus 2, and du over dx will be a negative 1 over root x. Okay. Now, it'll be 1 over root x. Now to find dy over dx, I know I'm going to find dy over du, which is 2u minus 2, and multiply it by du over dx, which is 1 over root x. That would be dy over dx, but there's still a problem. Dy over dx implies the derivative of y, where the independent variable is x. We have the independent variable x here, but then we also have this u. The u is a problem. What we can do is go back to our equation and realize that u is equal to 2 root x, and we can substitute that with 2 root x. So dy over dx is going to equal 2 times 2 root x minus 2 multiplied by 1 over root x. We can simplify it, or we can go ahead and substitute x is equal to 4, which is what I'm going to do. So we have 2 times root 4 minus 2 multiplied by 1 over root 4. So we have a whole bunch of 2's. 2 times 2 is 4, minus 2 is 2, times 2 is 4, divided by 1 over 2. Sorry, multiplied by 1 over 2. The answer there will be 2. So dy over dx at x equals 4 will give me 2.